Okay, so there's a question in the chat about how long is the presentation time limit for the final project. And just to make sure I don't misquote myself, I'm just going to make sure that I didn't already put this in the presentation. Yeah, okay, good. I did not already specify it in the presentation. Let's say that, let's pretend like you were doing a, I'll say that you should shoot for an upper limit of, like, pretend like you were doing this for a conference that, say, had a 12+15 format. So I guess I can maybe write this here. Now, of course, you're not going to have live questions. So I would say for the final project presentation, then let's say prepare 12 minutes of content maximum. And you should feel free to go under. Just make sure that presentation should be complete. And then see rubric attached to presentation assignment on Canvas. So no need to prepare 20 minutes or something like that. The idea is to have a concise presentation, no longer than 12 minutes, that captures the algorithm. So basically you're going to open it up and you're going to say, this is the algorithm that we were presenting, and then sort of explain roughly how the algorithm works. If you feel like it's important to give a little bit of history or relate it to some other algorithms, that's fine. And then go into a sort of a section on saying that, and here is how we're demonstrating its operation. Or if it makes more sense to interleave those and actually use your demonstration in kind of your exploration of the algorithm, then that would be fine too. But you basically don't need to give me all of the details that you would in your 4-page extended abstract. So you just want to sort of make an argument to an audience about that an audience that is educated enough to know about why these algorithms exist, but doesn't know anything about your particular algorithm. And so you're just trying to present it to them at kind of a high level and then demonstrate how it works, rather than getting into the nitty-gritty details of every single parameter and so on and so forth. So that's roughly the outline there. So any other questions about the presentation or the format? Okay. Great, and I might add to the, if I remember, I will add to the final project presentation instructions in that assignment so that it says this 12 minutes. But there is a rubric down there that that basically has a technical section and a presentation section that where I talk about you're judged on understanding the algorithm dynamics, whether you motivated the problem in your demonstration, whether you make logical conclusions about the algorithm, and then whether the presentation is complete. And so whether it is complete, that means that you kind of tell a complete story. You don't leave a lot of questions that are open. And so complete doesn't mean you have to leave every single detail. It's okay to sort of leave to the audience's imagination that some details have to be kind of filled in the engineering problem of getting things tuned or everything. But you have then presented an algorithm that you basically, if someone were to be confronted with that algorithm in the future, they would roughly know how that algorithm works and what problems are being solved by that algorithm and why that algorithm might be being able to be used and so on. So that's kind of what I'm looking for there. So with that, any other questions about the presentation? Okay. All right, so where we left off last time is where we got, this is our last neural networks content. And so we've been talking, if we think about sort of the evolution of where we've been talking so far, we started out with a single, we started out with sort of a motivation from the study of a single squid neuron. So it's a very, very long neuron, and someone named Otto Schmitt did a lot of the early work on that, and I think in the 1920s, and that motivated some of the and that there were some direct there was the sort of the original kind of spiking neuron inspired engineering adaptation was this Schmitt trigger, which had this hysteresis component to it, where it could fire and then stay fired even though its stimulus went away. And so you had to sort of have sufficient stimulus to get fired, but then once you were fired, you could remove that stimulus and it would stay stimulated. And that was sort of this Schmitt trigger, which was motivated by this neuron. But then even though there was that original kind of spiking inspiration, this exploration of neurons became very focused in the decades after that on the networks itself. Of course, the physiologists and the biologists and the neurobiologists were moving on sort of understanding the actual neurons, but the kind of computer science perspectives got focused much more on networks of neurons. And so what can you do? And that needed a single, computational unit. And that, so that gave us, the artificial neuron was, certainly very artificial in that it was basically just a generalized linear model, GLM, which gave you a way to map linear combinations through nonlinear activation functions to response variables. So it's just linear combinations get mapped through, I guess I'll say through nonlinear activation functions to response variables. And so problems like, so in computer science, people were interested in problems like regression and classification, which in other statistical disciplines, the classification problem is actually related to a nonlinear regression problem, where you're sort of like logistic regression, for example. And so so these problems in kind of data science are very much related to old school statistical problems in GLMs, where these activation functions here are akin to these link functions in GLMs. But then once you had this artificial neuron, then you say, well, okay, so in order for us to do classification problems, we basically have a regression engine that if we combine with the right activation problems, we can get, for classifications, we can use regression plus linear separability. And regression plus linear separability in data provides one way to do classification. So you have a bunch of data, you find a regression, and then that predictor that you generate effectively gives you a tool that maps any data point to a predicted output. And then you can use that predicted output to say whether that data point belongs to a class or not. And so, so that was one way to do classification, but it turns out the world is not linearly separable. So that's when we moved on to talk about radial basis functions, which allowed, or RBF neural networks, which basically said, hey, we can put, and we can create a layer, an input layer, that have a bunch of interesting activation functions within this input layer. So you've got your inputs and they go out to each of these radial basis functions. And then we can put our standard neuron after that. And so this is our whatever, this is our normal, neuron with linear weight, linear combo input. But these are our radial basis function activation functions. And this new input layer rescaled the space so that if you had data, if you had a class where, let's say, you were interested in separating inner from outer, so here's my inner class and there's my outer class on the outside, then that's not linearly separable. But if we take that space and we take radial basis functions, we can basically assign a radial basis function to the inner, and we can assign a bunch of radial basis functions to the outer. And so long as there is some overlap in these radial basis functions, and you can move the centers and you can change how sensitive they are, then you can end up covering parts of the space that do not, with these tiny little covers, and combine these covers to create classes which have different shapes than just a straight line. And so this whole radial basis function idea was was sort of the first way that we're using receptive fields to cut up a space so that each receptive field could then get linearly combined, so that if you weren't linearly separable initially, you've reshaped the space by covering it in little circles, and then said, all right, now that I've got these little circles that get activated under certain inputs, now can I get linear separability? So linear separability in the non-linearly transformed space. So radial basis functions extend, whereas one of the first ways you extend linear separability to nonlinear classification. And so that's one way of doing that. So, but then that also kind of shows that layers provide us more flexibility. So now we have an input layer and an output layer. And so then that says, well, what more can we do with layers? So again, we're sort of following the history of this development. Just because as I was kind of looking back through some of your muddiest points, just trying to see if we can kind of see where we are and kind of take stock of all that, which is why I'm kind of going through this brief summary as we get to the end of this neural network section. So with the radial basis functions, that sort of shows us here that layers are good. And so then people start experimenting with layers, and then we've got things like add hidden layers, and you get interesting structures like these multi-layer perceptrons, and then within that, then you can regularize those and create simpler structures like convolutional neural networks. And these convolutional neural networks themselves have their own receptive fields, which basically allow for layers to then wait to aggregate sections of an image. So if you've got some piece of an image, then you can assign receptive fields maybe with some slight overlap to them, kind of inspired by this like radial basis function idea. And each one of these receptive fields can get mapped to a single value or a single neuron in the next layer. And then that next layer's neurons can also then be grouped into other receptive fields. And so eventually you get to a layer that is looking at a giant picture, but that giant picture it's looking at in a very kind of blurry way. So it's not looking at one small detail, it's looking at aggregated details that have been put together. And it turns out that this way of cutting up the space provides more flexibility for learning algorithms to learn patterns. So it's just another way of transforming a space to make learning patterns easier by use of linear combinations and nonlinear activation functions. And so, so then we, played around with all these other things that you can do. Then, okay, let's add recurrency. And so that gave us recurrent neural networks. And then let's do interesting things with those recurrent neural networks, then say, well, let's create recurrent neural networks that have interesting dynamics that themselves are not needed to be trained. And so there's things like reservoir computing, where a random RNN is a filter that extracts temporal patterns so that they can be operated on by simple downstream, I'll call them decoding layers. So again, this trick of using transformations of the input in order to put it in a more amenable form so that downstream neural networks, which really are just nothing more than linear regression plus nonlinear activation. And so it's like this whole neural network thing is just how do we transform input data to put it into a form that is amenable to linear regression. And so that's kind of like, even in the recurrent case, that's where we see some of that happening. And then, we talked about different tricks that you can do once you have all of these tools. So unsupervised learning, supervised learning, autoencoders, et cetera. So, so that if we're thinking about things that you should keep in mind, you should sort of know they exist. The autoencoder structure and how it relates to things like PCA are probably good to know. And then just in general, unsupervised learning, supervised learning, reinforcement learning. These are all good things to kind of know the basic difference between. And so then finally we get to closer to where we are now. And so we learned that all of these, sorry to disturb, there's a question about the final exam. So technically your final exam, if you were in person, would be given on Friday of finals week. So since it's not in person, then you'll have at least all of Friday to do the final exam, or at least to start the final exam, and maybe time limited. And my hope is that I can have it available for the final exam period so that you've got flexibility during finals week. But, and if I can get it available sooner than that, then that's great. But my goal is to make it so that you have the final exam week to decide when you're comfortable to take the final exam. And then you can then choose to take it. And that's when the clock will start. And you'll have at least 110 minutes, which would be the normal final exam period, to do the thing at home. but it will be an exam designed to be auto-graded by Canvas. And so it's going to be similar to questions like you've seen in the concept check that you've been doing in Canvas. Okay. All right. So that was all with these kind of artificial neural networks. And then we learned, though, that finally coming back sort of full circle to the original neuron and the spikes that were studied by Schmitt, that there are these spiking neural networks and associative learning. And so, so we've been talking about associative learning. And a particular type of associative learning or mechanism for associative learning called Hebbian learning, which has a more technical name of spike timing dependent plasticity, or STDP. So that's a good term to know as well. And and so if we, why is Hebbian learning so interesting? So we have these, supervised learning, reinforcement learning, unsupervised learning. These are all things that we impose upon neural networks to try to get them to learn interesting things. But biological systems just learn. And so when we think about, yeah, so Swastika, you have a question from this section?
Yeah, I do. Would you mind if I just talk, because I'm just on Zoom?
Yes, absolutely. No problem.
Okay.
Go ahead.
So if you remember, you talked about a spike time dependent plasticity, where you had an example of the 5x5 grid, and you talked about the sound of the door slamming and the feel of the door slamming. They are two dependent things, and so they should wire together. That's what you said. But like, so isn't there something precursor to this, like that kind of already indicates that they're wired together, and then we ramp up the weights, or like it's just we just initiate it with random weights and it starts, or like there is already a pre-existing weight that's created? Because as far as I feel, like there should be something already existing, and we build upon that. Is it so?
Well, the idea behind learning associations is that if you have, so in those particular cases, if you're learning an association between a visual stimulus and an auditory stimulus, then the thought is that if you have the visual stimulus alone, there's going to be a set of neurons that will fire from that visual stimulus. And if you had the auditory stimulus alone, there'll be a set of neurons that would be firing to those. Now, if those neurons have chemical synapses between them, then there is an opportunity for one neuron's firing to make the other neurons more likely to fire. And so if it happens to be that I have, I've got vision and I've got audition, I guess, and I've got, this comes into a set of neurons, and then this comes into a set of neurons. And if there are neurons that, let's say if there are synapses between these, then if it happens to be that I always get vision and audition firing at the same time, then these synapses will strengthen. And what happens then is it will make these neurons in audition more likely to fire with weaker signals in audition if there is already a vision signal, and vice versa. And so when we learn associations, then it makes us more sensitive to one thing when the associated thing is present. and vice versa. That's just one way that associative learning could work. So the point is that you're learning a pattern. So of course the pattern has to already be in the inputs, and there has to be topological, and there has to be closeness between the neurons for neurons to learn that they should wire together. But if you already have enough potential, and I'll show that when I show a crossbar network here, as an example, when there's an artificial spike timing dependent plasticity. I'll get back to that example, and we'll see kind of an example in the artificial case on silicon, where you sort of set up all the potential connections, but only the connections that correspond to the patterns are reinforced, and that's how the learning works. But without those potential connections being there, then of course you couldn't learn it to begin with, because it's not like the neurons will, well, I mean, there might be some ability for this, but in general, it's not like neurons can crawl and find each other. They have to sort of already be close together before them to then beef up their sensitivity to each other. Does that answer your question, or did I misunderstand?
Yeah.
Go ahead.
Yes, thank you so much.
Okay, great, thanks. So, the beauty about the potential behind learning about Hebbian learning is that potentially if you can have artificial networks that learn by Hebbian learning, then in principle, they might be able to do everything. It just because in principle, we are, you know, we are doing all of the things that we're trying to make networks do, whether we configure them for supervised, unsupervised, or reinforcement learning. But we have one mechanism, and that is thought to be something like associative learning going on underneath it all. So, you know, the psychologists, and so there's already been some questions about this. So the psychologists view under associative learning, if you know, this is like from psych, you know, whatever the equivalent of psych 101 is, then, you know, you've got, there are two sort of major camps in associative learning that you hear about. The old school, you know, usually associated with Pavlov, classical conditioning. And in classical conditioning, you end up getting an association between a unconditioned stimulus and a conditioned stimulus that produces a conditioned response. And so the unconditioned stimulus is a stimulus that already produces a response. That's the unconditioned response. And then you take a stimulus that normally doesn't produce a response, but if that stimulus is always present when the unconditioned stimulus is there, the brain then forms an association between the conditioned stimulus and the response that came with the unconditioned stimulus, and that generates a so-called conditioned response. And so a dog's mouth salivating when it hears a bell occurs because it previously had a response where if it smelled the odor of a food, its mouth would salivate. And so if you pair the odor of the food with the bell, over time, the dog's brain will wire the experience of the bell sound to the salivation. And it'll get so strong of an association that if you remove the odor, then the bell sound is enough to generate the salivation. So that is classical conditioning. And so that for a long time was how psychologists studied learning. And that all came from, again, thinking that associative learning was enough. And so in these laboratory settings, then we can study the limits of classical conditioning and so on. And then when usually associated with Skinner, then that's when you have the more kind of sophisticated laboratory setups that we see more today, where you have operant conditioning. And I'm mentioning all this, and I'm going to get to this kind of philosophical point of like, why should we even care? We're an engineering class. Is that, I mean, the way I view this kind of, you know, what do we mean by bio-inspired optimization? To me, the question is not, how does this information help me solve a particular problem? The question should be, as we design systems, do I know enough to explain how this system, natural or artificial, solves a problem of interest to me? It is interesting to me to think about artificial systems that can learn how to make their way in the world. And at the moment, no matter how clever you are, we do not have any such systems that come close to what we see in nature. So we're not trying to build systems that mimic nature, because that might be the wrong design choice. But we don't even understand how nature does it. And so we shouldn't view psychology as that other discipline. We should view this as an approach to thinking about thinking machines. And they've already taken this approach, and this may be the wrong approach, but we should at least look at how they've done it first, because we may need to think about, do we need to set up classical conditioning or operant conditioning with our artificial systems in order to make them as good as the natural systems? Or do we at least need to understand what the psychologist got wrong, or why it doesn't apply to our systems? And that requires us to not think of it as psychology, think of it as an approach to thinking about thinking machines. So is this related to the causal condition topic? I don't know what you mean by causal condition. Maybe causal question, like coming up with a causal question for research. Let me continue, and then we'll see if you can clarify your question. Oh, and there's a if anyone's interested, if someone has put a link to a TED talk that I gave on how I believe the disciplinary structure in the university system is destroying innovation as we know it. And so if you're interested in my take on that, there's a 13-minute exactly talk that there's a link that thanks for sharing in the time there. All right, so operant conditioning. So this is basically an idea that there is an association between behaviors and reinforcement. So this is where reinforcement comes back into play. And so association between behavior and reinforcement. And this actually strongly relates to genetic algorithms, because there's kind of something similar that goes on here. And so the idea here is that we have a certain distribution of behaviors that we start at. You can think of it as a prior probability distribution. I could do any behavior right now, and I'm just going to pick one at random from this distribution. It's my prior distribution of behaviors. And by behaviors, I mean, I saw a red dot. Well, what do I do when I see a red dot? I could ignore the dot. I could touch the dot. I could touch a different dot. And if those are my three choices of the things I could do, I could pick equally among those three choices. Now what's going to happen is I'm going to do one of those choices, and then I am going to receive a reward or a punishment. And then I am going to associate my behavior choice with that reward or that punishment. And that association is going to then update my priors so that in the next time around, I change my distribution of behaviors. So we can view this as an association between behavior and reinforcement or punishment that leads to a change in the distribution of behaviors. So it is actually the association between the stimulus and the behavior that is rewarded. So we kind of view, some people will say this, the classical conditioning is sort of relates to involuntary behavior, and you might view the operant as voluntary behavior. And I link the operant conditioning to genetic algorithms because it's kind of like in genetic algorithms, you count on having some variance out there to try things. And then as you're trying things, then those different strategies that are being tried are going to get different levels of fitness. And the different levels of fitness will then end up reinforcing certain subpopulations more than others. And then those subpopulations become more dominant, just like those behaviors become more dominant. And so in theory, we get both of these things just from having associative learning. So if you have this mechanism of spike timing dependent plasticity, then in principle, you can put networks together that have the ability to learn in the classical way as well as in the operant way. And if we think about supervised learning, then in supervised learning, you can build supervised learning from this operant conditioning. So I can think of operant conditioning as leading to supervised learning. And I can view classical conditioning perhaps as leading to unsupervised learning. So rather than thinking this as involuntary and voluntary, I can view this as sort of unsupervised and supervised. And so in principle, with this one mechanism, if you know how to set your networks up correctly, you could, in principle, come up with ways to do effective supervised learning without thinking about like backpropagation. So we're not looking for ways to discover backpropagation. We're looking for ways to train networks without having to use backpropagation. Backpropagation was one way we arrived at supervised learning, but there could be other ways to arrive at supervised learning and through just having associative learning, having our spike timing dependent plasticity. There was a question about NEAT. NEAT is the neuroevolution of augmenting technologies, and NEAT is evolution applied to creating networks of different topologies, and so there. I mean, all the words kind of fit here, but I'm not sort of focusing on evolving neural. I mean, so NEAT evolves neural networks in a different way than here. We have a neural network that sort of has a bunch of connections that just need to be reweighted. NEAT is actually talking about how do we come up with whole new topologies. So you can almost think of NEAT as happening at an evolutionary time scale, coming up with different types of brains and then selecting the brains that you want. But what I'm talking about is at a life history time scale. How do you actually learn once you have that brain? How do you decide how to amplify certain connections inside the brain and attenuate others in order for that brain to learn something about the current environment? And then, yes, and that's a good question. A good point. A neural network evolved out of NEAT could still use backpropagation or weight adjustment. So, yeah, so this associative learning, we can view this as an alternative to backpropagation. And so that's really what I'm trying to get people to do when taking classes like this, is that I want us to be thinking about what's going on in a biological brain and what's going on in a backpropagation trained neural network and see where we can draw similarities and differences. And it may be that we can achieve many of the same ultimate functions by using different mechanisms. It may be that in the biological substrate, it makes the most sense to use Hebbian learning. But it may be that after we look at how Hebbian learning settles out, if we were to freeze the weights and look at what weights come out of it, you might get the exact same weights out of Hebbian learning that we would have gotten out of backpropagation. But then the question is, does our system allow us to implement backpropagation? And you might be in a system that doesn't have kind of the ability to implement backpropagation on the fly. Maybe you work in a more decentralized way. Maybe you can't quite organize the updating of the weights in the right orders and so on and so forth. So is there a more decentralized way to implement the training? And that is sort of why we're focusing on this things like Hebbian learning, is that it potentially allows for a decentralized way to train a brain so that it arrives at weights that are similar to the weights you would get in a more kind of coordinated way like you get with backpropagation. And I wouldn't say the backpropagation is the most efficient, because again, it's hard to say, well, what do we mean by efficient? So, I view when we look at nature, we're not looking to sort of understand we're not, it's all multi-objective. And so when you have multiple objectives and say centralization is one of them, energy efficiency is another one of them, or maybe the particular type of device you're using. I mentioned to you that backpropagation has been implemented in spiking neural networks, but it took kind of a little extra machinery to think about how to make that work. And it's not exactly a one-to-one map. And so are there alternatives to backpropagation? And this is just one alternative. In some systems, it may be better. I just posted onto the Canvas site under announcements an article that just came out of Google Brain. So a group at Google that does a lot of neural network development and research, where they have used a form of genetic programming to evolve. And so this is in the, so if you view the announcements, so in the Canvas announcements, there is an archived article. So it's a new article from Google Brain that they are calling AutoML-Zero. And so those of you unfamiliar with this form, AutoML is, you can think of this as automatic machine learning, which is a popular field right now, which is how do we get machines to develop their own machine learning algorithms. And so we just throw a problem to machine and it comes up with, and this does sort of relate to NEAT and similar. And so how do we get a machine to come up with its own networks that are efficient for the particular problems the machine wants to solve? And AutoML-Zero attempts to reduce the human intervention down to zero. That's kind of the hope here. And it basically uses genetic programming to design 3 functions called setup, learn, and predict. And then it has basically 64 operations that operate on scalars, vectors, and matrices. And it uses genetic programming, effectively genetic programming, to combine these 3 into different ways to program setup, learn, and predict. And so these subroutines are called in a kind of, so setup ends up generating, it uses mathematical structures to effectively build a neural network. And so it can instantiate matrices, and so those matrices end up becoming weights in a neural network. You can view it that way. And then learn is a set of functions which then operate on the variables that were instantiated inside setup. And so learn allows it to adjust those weights. And predict then runs the generated neural network, putting a data set that they have come in, and then it produces an output. And so learn can call predict, and it can then use the output that comes out of predict to judge how it should change things inside those structures. And so there is a consistent way that these 3 things are called at kind of an outer hierarchy, and they then end up producing a mathematical structure, which you can view as a neural network. And that neural network has a certain accuracy. So then they can then, instead of training neural networks, they train machine learning algorithms that themselves build neural networks. And so all of this is done symbolically. If that's symbolically, not numerically. So normally we think about, this would be like a normal ANN training, like ANN supervised learning. But this is done symbolically, again, via something that is effectively just genetic programming, GenProg. And so they use GenProg to then configure these 3 things. And then that ends up producing recipes or algorithms that themselves generate neural networks. And so inside the setup and learning recipes that are used there, you actually see backpropagation evolve. So they don't give backpropagation as an operation. They're able to show that this here ends up evolving backpropagation as a way to effectively update weights in a neural network. And so this method finds gradient descent and backpropagation on its own. They didn't have to give it to them. But then it goes farther and it finds ways to additionally improve those networks. So the question, I'm bringing the whole thing up here because there's this question, is backpropagation mathematically the most efficient in learning by adjusting weights? It's hard to answer that question, but frameworks like this one that just came out here from Google Brain suggest that backpropagation is apparently useful because it's found on its own by a computer that has not been told that backpropagation exists. But then the computer is able to find additional things that it can do that may be better than backpropagation. So it's hard to say if backpropagation is best, but we know it's darn easy to implement and it's darn easy to understand relative to other things. And it seems to work pretty well. Does it work best? Is it always feasible to use? Maybe not. So there was another question, are these networks that do reweighting through associative learning also described by simple linear equations like backpropagable ANNs? So if you apply Hebbian learning to a standard artificial neural network, it looks exactly like, so I'll just draw a line to make sure this is separated here. So going back, so Hebbian applied to ANN is you've basically just got a weight update at the next time step is going to be equal to a weight update for the weight at the previous time step plus some learning rate times whatever the previous value of the two neurons so we're interested, we have an I neuron that's upstream from a J neuron, and we're interested in adjusting the weights on the J neuron that correspond to the I neuron. And this general, so there you can come up with a general class of functions for weight updating. And so like backpropagation, for example, provides us one way to fill in this function. And so, so just in general, so we have weights that can be updated iteratively in a standard neural network like this. Backpropagation would fill in that highlighted F function in one way. Hebbian learning highlights that F function in another way. You could come up with lots of other ways that have an additive and iterative updating scheme, very similar to this one. I've just told you about two, backpropagation and Hebbian updating. So they certainly are related because they fit into this structure, but I wouldn't view Hebbian learning as backpropagation or vice versa. There's a question, how does one know that a concept like backpropagation has been discovered? It's not like it induces a chemical change that's visible, it's just numbers changing. How do we include that it's been discovered backpropagation? So I made the claim or the comment here that this process discovered backpropagation. And this is because they use symbolic evolution. So what they've done in here is that the output of this genetic program is each one of these things, set up, learn, and predict, are a set of steps, a set of operations. And if you then go and read those operations, you can then try to determine what those operations are doing. And the engineers that have manually gone through and read the operations that get evolved from these three, from setup, learn, and predict, if they go and they learn, or they look at the learning step here, then you can see that you can find that the steps that they do line up with what goes on in backpropagation. So you see that learn uses predict to generate an error. And then it uses that error to update the weights of the farthest of the layer most closely related to the output. And then from there, it calculates an error that propagates to the previous layer, and so on and so forth. So yes, the operations, the recipes that get spit out. So I just want to emphasize here, this is producing recipes, algorithms. These are readable. And because they're readable, then you can then actually try to understand what it has discovered. You can read the algorithms and then make inferences over what those algorithms are. And then maybe even get to the point where if you find something that doesn't make any sense at all, but works really well, then maybe you've now discovered a new way of doing something. So, so yeah, that's hopefully all that comes into, and then I thought I was trying to, I forget what I was exactly, who I was answering here, but this is, I'm trying to draw hopefully the relationship. So you can also put backprop in here too. So I'll say backprop to. Okay, so that's how associative learning compares to all of those things that we have been studying. It is just an alternative way to train neural networks. It's inspired by spiking neural networks, but it can be applied to artificial neural networks. But if we're in a spiking regime, for a while, it was the only thing you had to do, or only thing you could do. And now in a spiking regime, then now there is a way to do backpropagation, but it's almost like spiking would be more natural. And so that's what we'd like to sort of figure out in spiking neural networks. How do we just make use of the associative learning without having to lean on backpropagation? Okay, so, but I've been talking a lot about these spiking neural networks, and I wanted to then show you kind of these more concrete examples. And I started this example last time. So I mentioned that there is this, this nice article from Boyne et al. From not that long ago, 2017, in Nature Communications. And these are basically a bunch of neuromorphic engineers. So materials people, material scientists, electrical engineers that are making use of, so there is an electrical component called a memristor, which stands for, memory resistor. Turns out a lot of these names that end in ister are actually short names for things. Like, for example, a transistor is a transconductance variable resistor. So if you've taken a circuits class, you may have learned what transconductance is, and you may have learned what the variable resistor is, and what a transistor is combines the two of them together so that you get an element that provides you transconductance by way of changing its resistance in a variable way. Thus, transistor, transconductance, variable resistor. Memristor was similarly is a memory resistor. But whereas in a transistor, the resistance is changing to match an input signal. In a memristor, the resistance varies based on the current that has flown through it. So in a memristor, you basically have conductances or resistances that are plastic, term I used last time. And so that means that they remember their history. So if you run a certain amount of current through them, it will change their resistances, and then their resistances will stay changed. So they have this kind of persistent memory. And so they can act like weights in a spiking neural network with spike timing dependent plasticity. So the weights are also similarly plastic. And so, so the idea here is that if current is sufficiently high, conductance, which is just the inverse of resistance, will decrease. So you put a little bit of current in, and it's just going to act like Ohm's law. It's going to act like a resistor. You put a little current in, you get a little voltage across it. You put a lot of current in, and the resistance actually changes, it gets lower. And then when you turn off that current, the resistance stays low. So then if you put a lot of current in later, then you're going to get a different voltage out. I'm sorry, if you put a little bit of current in later, you'll get a different voltage out. So by running current through it, you change the resistance. And by changing the resistance, then future times where you probe that element then causes you to see the effect of the previous current. So it can act like a memory element. And so what the folks did in Boyne et al. 2017 is they built a, they basically built a spiking neuron out of memristor on silicon. So they basically created a device that is a spiking neuron that gets all of its cool properties from this memristance. I'm not going to go into all of the details of exactly how this device works, but you basically can think of it capitalizing on this fact that as the current increases through the element, it hits a threshold value that reduces the resistance. Similar to how in a spiking neuron, if the voltage goes up sufficiently high, then it causes a cascade effect which turns the neuron on. And so even if the voltage goes back down, then that neuron stays on. Or more to the point, it's like a synapse that was kind of insensitive to an upstream presynaptic neuron firing becomes sensitive to that upstream presynaptic neuron firing. And so they built one of these devices and then in an experiment showed that the physical device acted like a spiking neuron. And this in by itself is cool because previous spiking neural networks are built from view them as emulations of differential equation models of true spiking neurons. So in Boyne et al., they are actually building a device which spikes and acts just like a spiking neural network. Now they only built a couple of them, so not enough to be that useful. But what they did is they took all those device characteristics and they loaded them into a simulation model that simulated what's known as a crossbar array. And so how many people here? So by using the participants list, there's a button yes or no. And out of curiosity, how many people know what an FPGA is? All right, so under the participants list, there's like a bunch of buttons and there's like a little green yeses and red nos. Okay. All right, good, okay, that's good. All right, that helps me, that's good. Okay, so, so these are, this is a gate array, and this means field programmable. So, so basically, there's a piece of hardware out there called an FPGA that is able to implement any logic function you want without actually having to buy the logic gates. You just have these, you create these arrays of wires that cross other wires. And if you basically, and there's a way to then use a transistor to short circuit certain wires together and open circuit other wires. And by shorting and opening other wires, you can create whatever input-output map you want. And so it provides you a way to then generate to download a logic circuit to an FPGA and then reprogram that logic circuit in the field. So you don't have to then find a new NOR gate and then pop out your NAND gate and put the NOR gate in. You can go in and just change what's shorted together and what's opened, and then that'll end up changing all the input-output maps. So these idea of arrays with crosses have been very helpful in building hardware that can do things that in such a very flexible way. And so that idea is kind of mirrored here in a crossbar array, where they took a bunch of inputs. So you can view these as like pixel inputs, and they come down through this crossbar array. And we'll see where it crosses here in a second. And the inputs are coming vertically down into this thing. And then they have outputs that go across here. And so, and then at every junction, they put one of these cool memristor spiking neurons. And so so you can imagine that there's a weak, so you could say initially, there is a weak electrical connection at each crossing. And so you could imagine if there's if this pixel is turned on in an input image, then it will have a weak electrical connection to this output line, which will have a weak electrical connection to everything that it crosses by. But that weak electrical connection puts a little bit of current into there. And so if you've got your pixel inputs, which by the way, these have to be encoded as spikes, where a pixel that is more on, is more black, for example, is going to have a higher frequency spike, and a pixel that is more white is going to have a lower frequency spike. And so the idea behind that is that you're going to get these spikes of intensity. And so the pixels on, you get a lot of spikes down here, which generates a lot of spikes on this here, which then is going to affect the resistances of every cross that it goes across here. Now, what if you get 2 pixels turned on at the same time? If those 2 pixels are always associated, then basically the electrical link between that input and another input, between that input and the output and the other input and that same output, are going to be the most affected by this activity, because you've got activity going horizontally and activity going vertically, and you're going to get the most impact at these 2 particular points that cross. And so if you get this pattern over and over and over and over and over again, so that these 2 pixels are always associated together, then these 2 points, these points here and here, are going to get conductances that increase much more than the other conductances along here. And you can imagine then this happening all over this network as you put in different inputs. And so you keep presenting it inputs of different letters, for example. And so these letters have different amount of pixels, and then some letters are going to have certain pixels associated together, other letters will have other pixels associated together, and so on and so forth. And what ends up happening is that the input patterns. So again, you can view this as like, like there could be like an A, and maybe it kind of looks like this. There could be an O. It kind of looks like this, and so forth. Each one of these input patterns gets broken up into those pixel inputs and then tends to produce a particular output pattern, which might be, for example, the top bit will be high. And then we might get a different output pattern for a different pattern. And so persistent, consistent patterns on the input end up reconfiguring resistances at each one of these junctions so that you get consistent patterns on the output. And this happens in a totally unsupervised way. And so just by putting these wires on top of each other and just subjecting them with more and more of these input patterns, then just naturally, and it turns out very, very quickly, as they show in this paper, you get consistent outputs. And these outputs are even robust to input noise. So you can give it a bunch of patterns that look like an A, but some of those patterns that look like an A may also have a little bit of a pixel, an extra pixel on the side that's a little bit darker because it's got a little noisy. Or maybe one of the pixels on the inside is a little bit lighter because it's a little noisy. And so even though you get a noisy pattern on the input, it still ends up properly grouping it in the right output pattern. So associative learning has the way of effectively doing this kind of clustering, and it does it just by, in this, basically just a dumb set of these memristors that are laid on top of each other in an interesting way. So the topology combined with the spike timing dependent plasticity gives you exciting function that is useful on the output. And that's kind of what this STDP can do. And that's kind of a practical example of this. So there are questions about what I mean by that, about what Boyne et al. Has done with this crossbar array and this idea that we're getting pattern recognition. So I guess I should just write that here, pattern recognition via STDP. And you don't train the memristors. No, I guess you could say that they're kind of constantly being trained. It's just like the dog isn't trained to water its mouth. There's no reward. It is totally unsupervised. It just finds a pattern. There is an association, and the virtual brain just makes the association. It recognizes the association. And then, of course, later, you could then provide rewards. And maybe next time, as we motivate why we need other modeling frameworks like interacting particle systems, then we can talk about how things get really complicated when you actually add the reward systems in real brains. But even with dumb brains without rewards, you still can do some pretty powerful pattern recognition. Any other questions about this? You can view the memristors as the memristors are continuously changing resistances, where the resistance updates based on current through memristor. So there is no device going in and picking on a particular and saying, okay, you update. And then it's not saying you update. It's all happening in a decentralized, self-organized way. It's that the memristors start out and they all have one resistance, but the input creates more current through certain paths than others. And that pressure of putting more current on them causes all of the memristors in this path to then feel a greater urge to change their resistance. And so that asymmetric experience of all the memristors ends up updating the way in which the memrisistors actually connect to each other. Each one is a smart weight that updates itself based on, yes, that's correct. Each one is a smart weight that updates itself based on its past history of what signals it has seen. And in this memristor, you can view it as being triggered by anything coming down the horizontal path, as well as anything coming down the vertical path. And so that allows for a way that these things can become associated with each other. That's how this pixel becomes associated with this pixel and ends up together reinforcing basically over time. Whenever I see these two, then that basically is going to cause all of the current coming in from those two inputs to come out this output. And that creates an encoding where if I see this output, that must mean that this was the pattern that was in the input. So spike timing dependent plasticity has been known in biological neurons for years, decades, and then people over the last, say, decade or so have been building, well, actually, people have been building spiky neural networks in artificial systems for, I don't know, since the early 80s, late 70s, but it's really gotten more serious and more commercial in the last, say, 5-10 years. And building hardware devices that are at the level that are so tiny that they could fit inside very large scale integration. They could fit on chips like these memristors. That is very new. So again, this is from 2017. So this is Boyne et al. And that's in Nature Communications. All right. Well, that's where I'm going to stop things today. So we are going to move from neural networks into interacting particle systems and cellular automata for the next and possibly last unit. And then there'll be some relationships between the CAs and the neural networks and things like computability and such. So I guess I can hang around if there's any other questions. Otherwise, that's all I've got for you today. So you can feel free to pop off, and I'll see you on Wednesday.
Can I ask a question, Professor?
Sure, I can hang around for that.
It's from the last day's lecture where you talked about different frequencies encoding messages. We are going from a space domain to a time domain, and that different frequencies are used to kind of save information. So, is there a protocol that is used for this?
Well, I mean, there are a bunch of different ways to encode information in pulses. And so I mentioned a couple last time. So encoding information in pulses. And so, for example, there's pulse width modulation, or PWM, where you basically have a periodic signal that you know the period of. So you say this is whatever, 10 milliseconds, and you then encode the duty cycle is where the info goes. And so the duty cycle is the fraction of the total period that the up pulse is asserted. And so you might have a 10% duty cycle, which would mean that you're high for 1 millisecond and low for 9 milliseconds, and that will add up to 10 milliseconds. And so if you wanted to encode 15%, you turn the duty cycle on a little bit more, and so on and so forth. So that's one way to encode pulse width modulation. There's other approaches, like there's sigma delta modulation or encoding, which is a much more sophisticated way to do this. But so I won't go into a lot of the details, but if you just looked up sigma delta or delta sigma, sometimes it goes by, it adds a feedback circuit that helps to encode these things. And there are other approaches that use something called sliding mode control to generate pulses which encode information. And so both of these basically look at the output, and they say, they then decode the frequency information and then ask, is the decoded information close to what I want it to be encoding? And if it's not, they adjust how the frequency is set up. But I think, you know, if you're looking for a basic conceptual model, PWM, which there are circuits that drive motors that you can buy off the shelf that do PWM, is kind of the one to think about.
Thank you so much.
Mm-hmm. Any other questions?
Hi, Professor.
Mm-hmm.
I had questions on the type of research that your lab does. I was just curious. And personally, I've been like working a lot with deep learning and neural networks. So I was just curious on the type of research happening at school and also in your lab around things like that.
Sure. I mean, that might be a longer discussion or maybe more deep. So maybe that's a good one to hold off for office hours. So if you have sometime you would like to come to office hours, then we can talk about that sort of thing.
Okay. Your office hours are at 4:30 or?
That's right. That's right. So I will transition to my office hours room today at 4:30, and they're on Mondays and Tuesdays. So today included.
Okay. Cool. Perfect. Thank you then. Yeah.
Anybody else have any other questions about the content? All right, in that case, I'm going to stop the recording and in this room, and I will be back. Go ahead. Yep.
I just had one quick question regarding the project implementation.
Sure.
I was actually implementing harmony search, and the optimization function was actually a reward function. And initially, just to keep it simple, I was just giving the reward as 0 or 1. So it is kind of a step function, and the optimal answer is 1. Algorithm does converge to that point, but I'm not sure if I am doing it right, because it's a very small space to search for. But I was just experimenting around the algorithm, and so I wanted to verify if I'm supposed to change the function or something.
Well, it sounds like if this is a more specific question, maybe this also be something good for office hours. But I would say that, like, if your only two options are sort of are 0 and 1, but there's a lot of different ways that you could get 0 or 1, or maybe there's a lot of ways you get 0, but only one way to get 1. I mean, a good way to tell if your algorithm is working is to compare how often it gets 1 based on a random search. So compared to a random search. And so if you were just randomly to choose an outcome, how often would you get 1? And how often does your algorithm get that? And if your algorithm gets it, like, you can use a chi-squared test or something. And so if your algorithm gets the right answer much more often than a random search does, then it suggests your algorithm's doing something correctly. So, but okay. You probably, go ahead.
I can explain you during the office hours. I'll come in today. What exactly I have done and what is the output I'm getting. It would help us clarify and resolve this thing.
That sounds good.
Professor, okay. I would like to join your office hour as well. So, what is the meeting number for it? Would you have, like, is it shared?
It's on the Canvas site. So if you, I don't have it off the, but if you just go to the Canvas site, right on the main page, it has the link.
Sure. Thank you so much.
And if I'm already in with somebody, it'll put you in a waiting room, and then I can accept people out of the waiting room as people cycle out. All right. So with that,
Well,
I am going.
I would like to hear about what your answer to Valeri's question as well, about what your research is on. I'm kind of
Okay.
if you
All
can
right. Well, I
explain.
might. Well, all right. Well, I'll. If I see you and him in the office hours at the same time, I'll bring you in at the same time. Then.
Thank you. Thank you so much.
Sounds good. All right. So in that case, I'm going to stop the recording and close this room, and I'll see everybody else on Wednesday.